Good morning, students. Happy Friday to you. It is Friday, 5/15/20. Wow, halfway through May. I know some of you are having some struggles and time seems to be creeping by for you, but boy, that's not my experience. Time is flying by. Hope that you're doing okay. As always, if you have questions, please let me know. And just maybe pop in and chat with me sometime on Zoom. I'd love to see your faces again. Say hello, even if you don't have questions. And if you do have questions, I can help. All right, where are we at? We're going to start a new mini unit, and I'm going to put our learning target for today. The basic target is I can describe the chemical bonds of a water molecule. What do we have to know to describe the chemical bonding in a water molecule? So, Unit 8, I'm going to call this water. And we're going to take, this is a real treat, we're going to take just a little of a chemistry approach to this one. I love chemistry. Maybe some of you will too. Alright, so in your notebooks, I want you to write down the formula for water. I bet you all know it. I'll wait. If you need more time, pause the video, but I think you should have the formula for water. H2O. How many of you got it right? Good for you. All right, so next question. What does it mean? I want you to think about that. I won't make you write that down, but I want you to think about it for a little bit. If you still need to think, pause the video. Hopefully this is what you came up with. Each molecule of water has two atoms of hydrogen. So the two, this by the way is called a subscript because it's written a little bit below the line. Sub means below. Okay, a subscript 2 refers to the element right in front of it. So H refers to hydrogen. The 2 refers to the H. Now there's nothing behind the oxygen, so it's implied that it's a 1. So there's two atoms of hydrogen and one atom of oxygen. Great. Now, I want you to draw a picture of a water molecule in your notes. I'll wait. If you need more time, pause the video. But let's go on. What does our picture of water look like? Anybody have a picture that looks a little bit like a Mickey Mouse face? The oxygen and the two little hydrogen ears. I bet a lot of you have seen that before. So, why? Why does it look like this? Or like this? That's our question. And we're going to have to get into the chemical bonding for that. Why doesn't it look like this with the ears on the side of its head? Or why don't we have the hydrogen in the middle and hydrogen and oxygen on the outside? So it's about what's happening with electrons. Let's back up just a little bit. Atoms are made of 3 main subatomic particles. And I can promise that you've had this in some previous class. So hopefully this is just a little bit of a review. 3 main subatomic particles. We have protons, which have a positive charge and are found in the nucleus. The nucleus is the center of the atom. We have neutrons, which have no charge. They're also found in the nucleus. And we have electrons, which have a negative charge. And they're found in the electron cloud, which is the outside of the atom. So these two are found clustered in the middle, and these are found around the outside. Make sure that you stop here and get that written down, a little chart. One common mistake that I get some students making, most students seem to get the protons are positive. The prefix pro means positive. I'm pro chocolate, way too much pro chocolate. But then some students go with neutrons, and I guess because maybe the It begins with an N. They go with neutrons as negative, and neutrons, it's almost the word neutral. Neutrons are neutral. They have no charge. Electrons are the negative particles, and that's really important. All right, so let's talk about a hydrogen atom, because water has a couple of hydrogen in it. And I'm giving you some basic information. A hydrogen atom has just one electron. But it wants a second electron. It wants to get to 2, so it wants to gain one more. So here's my little picture of a hydrogen atom. So the proton's going to be in the middle, and out here on the outside it's got one electron. And it wants one more. So what if I have 2 hydrogen atoms? This guy wants another electron. This guy wants another electron. So, imagine you're this hydrogen, and you look out, and you see an electron over there, and you want to grab it. And you're this hydrogen over here, and you see an electron, and you want to grab it. So what's going to happen? Watch this. Probably wouldn't believe how long it took me to work out that little bit of animation there. But I imagine both hydrogens, they both want an electron, they both reach out and grab. But here's the thing, the other atom doesn't want to let go. So when they pull together, pulling on each other's electrons, they effectively pull themselves together, and now they're kind of stuck together because they're both grabbing onto the same electrons. Okay? Picture that like, here's an atom over here that's grabbing hold of electrons, and here's an atom that's over here and it's grabbing hold of electrons. And because they're both grabbing the same electrons, they're stuck together. So this is called a covalent bond. Just to get into the word a little bit, co means together, and valence, energy level, refers to the outermost electrons. So this is kind of saying they've put their outermost electrons together. So, huge definition right here. A covalent bond is a shared pair of electrons. This atom wants them, this atom wants them, they're stuck together. Now, the definitions are always written out as a shared pair. I myself think that that's a really kind of a warm fuzzy way of looking at it, where truly it's a tug of war. Both atoms want the electrons. They're both pulling on the same electrons, and neither one wants to let go, and they're stuck together. I don't know that it's just a friendly sharing, but this is the result, is that they're locked together. All right, so let's come back to our water. So this guy doesn't work. And the reason is, if you took this hydrogen and you bonded it to this hydrogen, okay, they're sharing a pair of electrons, there's now no other electrons to interact with the oxygen. So a hydrogen, having only one electron and only wanting one more, can only pair up with one other atom. I can't, in this diagram, I'd have to have the hydrogen sharing something with this hydrogen and sharing something with this oxygen, and it doesn't have that. It's only got one electron to use. All right, now why not this model? Why do we always draw our water, looking like Mickey Mouse with the hydrogens up there? Why not draw it down there? And that's a little harder to explain. So let's look at our oxygen atom. Now, oxygen has 8 electrons in total. Okay, that's total. But of those 8, 6 of them are on the outside. Okay, 2 of them, the electrons are arranged in levels, and so 2 of them fill up this inner level. And once we start putting electrons in the outer level, the inner ones aren't really involved in bonding anymore. So it's just the electrons on the outside of the atom. And that should make sense, because if 2 atoms bump into each other, it's the outside that bumps in. So there's 6 electrons on the outside of oxygen. And I want you to think of them as 2 pairs and 2 singles. Maybe you're picking up on it already, but the single electrons, that's where we want to do something. what oxygen would really like is 4 pairs. So where there's a single electron, that oxygen wants to grab another electron. And where there's this single electron, it wants to grab another electron. The oxygen wants to fill up this circle with 8 electrons. So what if, here's a friendly old hydrogen, and it's got its 1 valence electron, and here's oxygen. Now, hydrogen wants another electron. So hydrogen looks over and says, hey, there's an electron, let me try to grab that. And oxygen wants 2 electrons, but it says, well, there's 1, let me try to grab that. And so our hydrogen and oxygen might try to take the electrons away from each other, and as a result, they get locked together by sharing a pair of electrons. Okay, think back. What do we call a shared pair of electrons? I'm waiting for you. A shared pair of electrons is a covalent bond. Okay, those 2 atoms are covalently bonded. But look, there's another single electron. So oxygen wants 1 more electron. Where in the world could it get it from? Well, what if there was another hydrogen nearby? This hydrogen wants an electron. It says, hey, there's 1. Oxygen wants an electron. It says, there's 1. And they both try to grab them. And I don't have this animated nice, but just imagine they both try to grab on. So a shared pair of electrons is a covalent bond. Do I keep repeating myself on that? I think I do. Maybe that's significant. Okay, so how many bonds did this hydrogen make? Hopefully you saw 1. How many bonds did this hydrogen make? 1. How many bonds did the oxygen make? 2. Those. Now, if I took that model that I just had here and I rotate it, doesn't that kind of look like our Mickey Mouse head? Now, I said this gets a little bit tricky because could I have drawn my oxygen with its electrons here and here, and then a single electron here and a single electron here, and then could we have our hydrogen come in with 1 electron here, and our hydrogen come in with 1 electron here, and doesn't it look like that other one? So we're still not there yet. And the problem is that this board is flat. And so when I'm drawing stuff on here, it's not a true representation of how the atoms actually are. Because atoms are not necessarily flat. So on the board, when I want 4 pairs of electrons, I draw them on top, bottom, left, and right. But really, 4 pairs of electrons, let me show you a model here. Really, 4 pairs of electrons don't go top, bottom, left, right. They go towards the corners. Let me show you this. Here's a model I made out of paper and tape. This is a 4-sided figure, or a 3-sided pyramid, but it's got 4 sides all together. It's called a tetrahedron. And so the electrons on that oxygen are trying to point towards the corners of the tetrahedron. And maybe you're asking yourself, why? Electrons are all negative. They don't like each other. So they want to get as far apart from each other as possible. And the furthest you can get apart from each other and still be attached to the nucleus is towards the corners of a tetrahedron. All right. Now, let's imagine 2 of those atoms that are bonded, or 2 of those pairs of electrons here have hydrogens attached, and 2 of them are unshared pairs. They're just a pair of electrons. So what we're looking at here is kind of like this. Okay? Now, could I have shown it like this? And then if I drew it that way, Doesn't it kind of look like this guy? So the problem is that it's not exactly wrong. It's not at all wrong to draw it that way, but it's misleading because it makes it look like the oxygen is just sandwiched right directly in between two hydrogen. And if we think about 3 dimensions, it's not. So this is a better representation of what the water molecule actually looks like. Okay. We're almost done. So, all right. So I'm trying to draw my tetrahedron, a 3-dimensional shape, on a 2-dimensional surface. And, so I think showing you the actual model here was probably a little bit more effective than this. So this would be kind of looking at it like this. So we've got this molecule, and the shape. The reason the shape is so important is because it has this kind of unbalanced part where the hydrogen are both on one side and the oxygen and the other electrons are on the other side. We've got to add in something. Oxygen attracts the electrons more strongly than the hydrogen. So remember, I said that the covalent bond is kind of like this tug of war. Both atoms are pulling on the same electrons. Oxygen is stronger than hydrogen. It has a stronger attraction. And so it doesn't quite take the electrons away from hydrogen, but hydrogen's sort of losing the battle, so the electrons spend more time by the oxygen. I compare it sometimes to, like, let's imagine that you and I bought a car together. I get to use the car every day from 6 a.m. to midnight and all weekend long, and you can use it the rest of the time. That wouldn't be an equal sharing of the car. Okay? We got an unequal sharing. The electrons spend more time by oxygen. And what that does is it means that the oxygen part, electrons are negative, and if those negatives are getting pulled a little bit this way, the oxygen becomes a little bit negative. Now I'm using this weird symbol here. It's a lowercase Greek letter delta, and in this context it means partial. Okay? So people in chemistry are too lazy to write out the word partial, so we use one Greek letter. Some of you are lazy. This is probably a way to go. Okay? But we have to understand what the letter means. You can't just write down any letters you want. In science, this has been established that this means partial. So this side, this atom over here, because these electrons are pulled this way, this side of the molecule is a little bit negative. And the hydrogens have had the electrons pulled away from them, so they're a little bit positive. And if I draw a line through my molecule, I could draw my line like this. I could say that the hydrogen side is a little bit positive and the oxygen side is a little bit negative. All right, so pop quiz. Which diagram best shows the charge distribution on a water molecule? So, do we take our Mickey Mouse face and cut it right down the middle and say that side's negative, this side's positive? Do we draw it horizontal with the ears on top and say that the ear side, the hydrogen side, is negative and the bottom is positive? Do we split it in the middle and say the left side is positive and the right side is negative? Or do we split it horizontal and we say the hydrogen side is positive and the oxygen side is negative? Think about it. We just had it. I'll give you a hint. The answer is D. That's a big hint. Okay, yeah, the hydrogen side is positive because hydrogen has less attraction for electrons than oxygen. And that's as far as I wanted to go for today. So I'm going to have you do a little worksheet answering a couple questions on what you just watched, and we'll pick up on Monday. Have a great weekend.